I view this essentially as part of an advanced standard model code. In fact, it's a completion of a course on the standard model. Of course, at a certain point, obviously, I will discuss models, okay, because models are essential to get to even know what we are talking about, okay. But I will mostly be the main goal is to try to give a perspective on the problems, okay. And I'm well aware that this sounds, the risk of becoming vague if you just want to give a perspective is very serious. I'm aware of that. And because of that, I will try as much as I can to come up and present little examples of what I'm talking about. So try to give concreteness, okay? And so, yeah, concerning models, in the last few decades, in fact, approaching the LHC, it's probably fair to say that maybe we did a bit too much model building, okay? But in the last decade, I think we have been doing too little, okay? So I think we have to find something in between. Now the emphasis is, particularly in particle field, I mean, there is an emphasis on solving some specific question like dark matter, focusing on the axiom. But largely the core of particle physics is being left in the standstill. Okay? Apart from some work that aims at great generality, since we don't want to talk about models anymore, we just discuss general features, effective theories, effective theory of the standard model, but without making any assumptions, and I think assumptions are necessary. Because after all, what is model building? Model building is just the exploration of the space of hypotheses given a given problem. And in fact, even the difficulty in addressing the problem is important, and there is much to learn. In a sense, the problems are defined by our failure in trying to solve them. And in a sense, my course is about that. Okay. So let me cut short this introductory discussion because I don't know where I'm going. So let me outline the content of the course. Okay, the course is essentially an extended version of the colloquium I gave here last fall, and also I gave 2-3 years ago at Columbia. Okay, so it's essentially divided into 4 parts. The first part, if you want, is an ideological part. It's the effective field theory. It's a model effective field theory ideology on quantum field theory. So this part is utterly basic, okay, and it's truly aimed at the students, okay, and so the basic idea here, the main goal of the section is to emphasize and to make it as clear as possible that in spite of all its complications, which I will be cleverly avoiding, quantum field theory, or effective quantum field theory is essentially the same as all other constructions in physics that you have seen before. Okay? In a sense, everything we have been doing, you have been doing since the beginning of your studies, is an effective description of physics. And quantum field theory, in spite of all its deep, sure depth, apparent or even substantial depth, is just yet another example of that. And I'll try yeah. And essentially the story is that whenever you do physics, you're describing dynamics phenomena at a certain length scales, profiting from the possibility of remaining ignorant or mildly knowledgeable. See, with a mild knowledge for what happens at much shorter distances. That's always the story about when we do physics, right? We have phenomena at some large distance, we describe it in terms of few parameters. That's a bonus because we can do things. The other side is that we don't know what happens at shorter distances, but that's precisely the two different faces of the same matter. I'll try to emphasize that with examples. The second part, so this sets the stage for later understanding the standard model. The second part concerns symmetries, in particular, and selection rules, accidental symmetries. I mean, and then selection rules, with a little emphasis on the fact that symmetries are important, but they are, when they are exact, but in a sense they're even more important when they're broken, and because they give, the breaking of the symmetry gives us control on the structure of the dynamics through gives us control of how certain parameters appear in the dynamics, how they affect it, and just emphasizing here that dimensional analysis and the use of SO3, say in atomic physics, they're very much conceptually the same thing. Okay. And then this will lead to the notion of naturalness or of naturalness. So, yeah, this is the preliminary part, okay, in a sense largely, and I don't mean any originality here. In fact, of course, I don't mean any originality. And for those who are senior here, I am a bit embarrassed because I will be saying things that you guys know very well. Maybe even the students, but I think for the students I can take my shot at. Perhaps, yeah, that's aiming at that, okay? So the third part is the part which I call behind the standard model, and consists in analyzing the structure of the standard model and how that structure matches phenomenology in the light of the concepts introduced before, okay? And essentially this is viewing the standard model as an effective field theory. Normally, by standard model, we mean, or many of us mean, the Lagrangian that fits in the t-shirt that is sold at CERN, okay, where there are essentially all the things that we have observed in collider experiments. But actually, that is like the tip of the iceberg of a bigger structure in which you think of standard model as an effective theory, where essentially you have everything. Okay? It's just an infinitely long Lagrangian. What I'm saying is that, and to understand that Lagrangian that appears on the t-shirt, I think it's important to understand also all this rest, all this background. In a sense, you can make an analogy. The Lagrangian of the t-shirt is like the Mona Lisa, and the rest is like the background. Okay? If you don't have that background with that nature and that primeval stuff, I don't see, I mean, the Mona Lisa loses completely this contest, okay? So I'm trying to contextualize it that way, okay? And contextualizing this way, I will emphasize the pluses, which are many, and the minuses, which is essentially one, or if you want to extend this course, a few, 2 or 3, okay? But in this course I will focus on one, which concerns the Higgs mass, okay? And trying to understand how fixable, again, exploring in theory space, how to fix the minuses, I will come to the final and fourth part, which is the beyond the standard model part, the genuine beyond the standard model part, where I will discuss some of the basics ideas to fix the minus of the standard model, compositeness, supersymmetry, and discuss their minuses, okay? Or the effort you have to do, the effort model building, but it's genuine, I mean, conceptual effort to compensate their minuses. And in a sense, this situation where you have some minuses here, some pluses, and here the other minuses, it turns out they are essentially complementary, defines what I call the hierarchy paradox. So that's the essence. By the way, normally a course on BSM, as I said, starts very quickly, talk about the problems, and then you go quickly here. And again, I don't think this is the optimal way of introducing this field of research. In a sense, it's like going directly to the Mona Lisa of Andy Warhol, okay? And the Mona Lisa of Andy Warhol without the Mona Lisa of Leonardo doesn't mean anything, absolutely nothing, okay? So this is why it's going to take a while before I get to that, and hopefully I will get. Now, the course is going to be given at the Blackboard, so I've already given this course 3 years ago with slides. I'm not entirely sure, in fact, I'm pretty sure I will not be able to do everything on the Blackboard. So at a certain point, every day, when time starts running, I will switch to slides. Hopefully, I'll try not to, but I'm afraid I will have to. Okay. Very good. Okay, so I think I can start. Okay, so let me start with this first part. So I have already presented these things in my colloquium, so I am aware of the risk of redundancy, but maybe not everybody was there, and so for logical coherence, I will do. So I will be talking in this first part. I'll be concerned. The essence of all the discussion is length scales, short and long. Okay, and just to touch base. Okay, we're in the context of relativistic quantum mechanics, quantum field theory, and the laws of physics give equations, and the equations equate different quantities, F equal ma, and then as soon as you write F equals ma, you know which units of measure are assigned to force. Okay, it's mass times length over time squared. Okay. Similarly, the equations of relativity in quantum mechanics allow us to identify some units of measure, in particular relativity identifies energy and momentum because there's a fundamental speed, and quantum mechanics identifies momentum with the inverse of the wavelength. Okay, this is the probability waves. So put it together, relativity and quantum mechanics in relativistic quantum field theory, we can work with only one unit of measure, which can either be energy or length. Inverse length is energy. Studying microphysics means going to high energy. This is why we are interested. This is why the normal high energy physics, maybe short distance physics would have been more adequate for the public. But okay. So, when you consider physics from the point of view of length scales, there are two notions that are essential. And the two notions are the notion of universality. I don't know, maybe there's another way of calling these things, okay? There's perhaps a clever way. This is the way I call it. One is universality, the other is reductionism. Well, reductionism is the idea, is the concept that to understand how things work, to understand better how things work, you have to look inside. You see a radio, how does it work? You open it, okay? That's the basic idea. That was the essence of a great part of the progress in science, physics, biology in the last centuries, last 3 centuries. And the other notion is universality. Universality is the other side of the concept. Universality is the fact that even if you don't know string theory, you can still do physics, essentially, right? If you're describing physics at a certain length scales, okay, it's a practical thing. It's a fact that when there are separation of scales, and these exist, you can live with, you can perform physics with a minimal knowledge of what happens in short distance. In other words, you can parameterize physics with a finite number of parameters, even if you don't know everything. Okay? In other words, physics, we can do physics. That's essentially the reason. And let me illustrate this dichotomy or the balance between these two things with examples. Okay? The simplest example where these two notions are exemplified is the multiple expansion in electrostatics. Okay? I'm using these concepts because I want to insist on these very intuitive aspects that by the time one has studied introductory physics and at the level or beginning PhD, these things are well acquired. And when you arrive at quantum field theory, everything seems a little bit more fuzzy and harder to understand. And I would like to insist on the fact that this is the same thing. So this is why I'm starting with these very elementary examples. By the way, this course is not a technical course. It's in a sense, it's a meta course. In that sense, it's harder to give than a technical course. A technical course, it's a piece of cake. Here you have some equation, you have to prove things. Here, it's a bit harder to get. Anyway, because I'm trying to tell you a story. Now, then stories are stories. So the multiple expansion in electrostatics, so what is the idea here? The idea is that you have some distribution of charge localized over a distance of order A, okay? And for some reason, you're considering the electric field or the potential at a much larger distance. In this situation, you can write your potential, which is the integral of the density over the distance, okay, in an expansion in multiples. Okay, so the starting one is the monopole, then the second one is the dipole, which is a vector. Monopole is just a scalar. The dipole is a vector. Then you get to the quadrupole, that is a symmetric traceless matrix, and so on. Okay. This does not move, right? And so on. And what is this? Well, generically, modulo cancellations, this object here, okay, given this is just the total charge Q0 is just the total charge included in this region. The dipole will be of order, generically A times the total charge, or in any case, A times some finite charge, which could even be bigger than the original one, but anyway, it's proportional to a length, okay? It's controlled by a length. The quadrupole is controlled by a length square, and so on and so forth, okay? So this expansion in quadrupoles at long distances is an expansion in powers of A over R, okay? Here you get 1 over R, sorry, cube here. 1 over R squared, this is 1 over R cubed. Not 2 powers of R above there, so this is 1 over R A over R squared, and so on and so forth, okay? So you have a smaller and smaller contribution as long as you are at distances that are sufficiently large and you work at finite precision, because you always work at finite precision, you will not need to keep all the expansion. You can truncate it. Let's say that your precision, let's say A over R is 10 to the minus 3, but you have a precision in 1 part per billion, then you can go to the optical, the one that comes behind that, okay? So at every order, you lose 3 orders of magnitude in size, but if your precision is high, you can go up to there. And the crucial thing is that with finite, that even if the original charge density, which is a function, and a function contains infinite, is defined by infinitely many variables, the quadrupoles are just numbers, the multipoles are just numbers, okay? And at the fixed level of precision, you only need finitely many of them, okay? So at that order, okay, if you're far away, if you have finite precision, which is, finite precision, it's a given, it's always the case. Being far away, well, in this particular case, it's up to you, right? You may be far away. You may be in a room and you may not be able to go far away, but let's say that you can go far away, you are giving. In fact, in all the cases, we will always need to be able to go far away, and you'll be clear what that means later on, okay? So if you can go far away, then you are in this situation, and you can describe physics no matter how complicated it is. I mean, no matter what the physics is, you can describe in terms of finite number of parameters, okay? So let me say it here. Fixed accuracy. For R going to infinity, finite number of parameters. Okay. So and this contrast of infinitely many parameters and finite here just also implies that you could have that for any given long distance field, okay, characterized by a few multiples, this can correspond to an infinite variety of microscopic physics. Okay, so you have that very different low energy short distance distribution of charge can, when measured at long distance, look the same. And this is the notion of universality. In fact, if you take the very extreme case and you go very, very far, where you can only measure the monopole, okay, then all the complexity you have in rho is reduced to just a single number. Okay? And all these different things are universally going to be described by just a number. Okay? So the universality, so this is the notion of universality, is both ignorance, because you don't know an infinite amount of notion, but the fact that, in fact, that with that finite information, you can make predictions in the following sense. Imagine you are at a certain distance and you have a finite precision, and you do a finite set of measurements, and you measure all the relevant multiple. There are finitely many of them. For instance, if you go up to the quadruple, you have 5 here, 3 here, and 1 here. You have 9 parameters, okay? And with that, and with these 9 parameters, which you can measure by measuring your field in a particular region, of course, in some region far away, okay, here, okay, then with the assumption that the charge is localized, then you can expand this all over the place. Of course, you have to make an assumption, because it could be that now you try to predict what happens here, and here, precisely where you're measuring, there's a tiny little charge, almost infinitesimal, but you go on top of it, okay? So then you will not predict. But this is the same situation if you think when you do particle physics, like measure the standard model. We have measured the parameter of the standard model, and then we can make predictions here and there, but maybe there is some tiny, very weakly coupled particle that we cannot see because it's very weakly coupled. And in another experiment where this particle goes on shell, creates big, okay, and then we see it, okay. But again, that's always possible. So what this is to say that in order to take the step where you expand here, you always need to make assumption. But that's always the case. Okay? There was a question somebody asked me when I gave my colloquium about the magnetic anomaly of Earth, but that's precisely the point, okay? But that's like in the rest of physics. If you don't make assumptions, you don't go anywhere. Then the assumption, you can test them, but that's essential. On the other hand, when R, so let's say large, when R goes to small, and if you get closer, then and with fixed accuracy, okay, then the closer you get to the distribution in observing your field, the more multiples you have to add to match your accuracy. Okay? And at a certain point, when you reach distances of order A, then this expansion breaks down, and you can no longer describe the potential in terms of a finite number of variables, and infinitely many of them. At that point, you're sensitive to the very function. This fact that when you get closer and closer, you learn more and more about your system, well, that's the essence of reductionism. Okay? So here you access more and more parameters. So you learn more about what this thing is, right? You can start, maybe, I don't know, you start, you see a monopole, then you see a dipole, and then you go on, you get closer and closer, and you realize that with your accuracy, the quadrupole is 0, the octupole is 0, then you say, oh, maybe this is just a dipole. Okay? So you get more information. And this is the notion of reductionism. But you see, they are very much tight, and they simply correspond to going close and going far. And as soon as you get to distances shorter than A, you go inside. Well, then what can happen? Well, it can happen that this is just some ugly distribution, some without any structure, but it could happen that you discover that this distribution has some very peculiar, I don't know, form with some geometric features, okay? And then you start all over again. Then you're now inside here, and now you restart a new expansion, getting closer to those points where the charge is localized. Okay, so this is, and so this example is the cartoon, I would say, of basically all of the physics that I have been doing all my life. Okay, they're all variants of this. This description, in terms of very few multiples, is what we call an effective description. Okay, and in a sense, eventually we will equate the standard model to something like that, where we have some finite accuracy in our experiments, and we have only measured the first few multiples, but there is this huge ocean of stuff which, for some reason, we have not yet accessed. And the question is, what does that mean? Okay. Now, in the case of so here the example I presented is is static, okay? This is static, okay? So here I'm only talking about length. There's nothing moving, everything is at rest. But this example, this situation extends to dynamical cases, particularly remaining within electromagnetism. It extends to the case where you're considering the emission of radiation. There also you have multiple expansion, different nature, but it works conceptually at a very bare bones in the same way. Another example, which is truly a textbook example of effective description in the dynamical situation, is given by fluid. Okay. Okay. So what is a fluid? A fluid is a situation where you have some small entities that can be molecules, they can be atoms, they may be, well, I don't know if there was an interactivity, hard balls. Gravity is a big different thing, but you could say also something, it could be some interacting dark matter, okay, to some extent. It can be quanta in a hot QFT. Anyway, there are some elements, okay, that some point-like entities, if you want, that interact, and their interaction, there are many of them, they fill the whole room, and if you look at short distance, you see the interaction of all these guys, okay? And so, but there is a typical, and this interaction is as messy. What's going on at short distance is as messy as hell, even if the laws, the general microscopic laws are simple, but what happens? It's complicated because there is a lot of data, okay? There's a lot of stuff. But there exists, okay, a length scale, which is the length, the collision length, okay. And if you want a time, which is the collision time, beyond which, okay, you can afford a coarse-grained description where you essentially average out all this microscopic motion, and you buy yourself a more ignorant, a picture that is ignorant of all the mass that happens at short distance, and only relies on a few macroscopic variables, which are in a sense the analog of these multiples. Okay, and in this case, these macroscopic variables are the density, the pressure, and the velocity of your set of particles, which is now treated as what we call a fluid. Okay, and so in this regime here we have the fluid regime, and this the regime here we have the point particles. Okay, and let me see what I forgot to say something. Yeah, sorry, this is, I should have said, this is individual. These were the right words I forgot. This is individual. Here you have to follow individual particles, and what you have here is, here you have the collective behavior. Okay, and now, the collective behavior expectedly should work the better, and the better, the more smooth these macroscopic variables are as compared to the crucial length scale that characterize this wall of fire between the macroscopic and the microscopic, which is essentially, this wall of fire is the same now here. These two lengths here, length and time, are the analog of this length here. Okay. And very much like here, okay, where the expansion, where your expansion was in positive powers of the small length, here you also expect to have an expansion in positive lengths of these variables, okay, of this crucial length. And here the analog is that the analog of the monopole, okay, is the perfect fluid, or if you want Euler equations. Okay, this is the monopole. It's like the leading, the absolute leading term, okay? And this is just Newton's equation for a perfect fluid. dT P plus rho, so like this. Equal minus the grade of the pressure. Okay, so this is your analog of the perfect fluid. But you see now you must expect the existence of corrections to this equation that are controlled by positive powers of some length or some time scale, which are the natural length and time scale of the situation where you are, which is the collision time, the mean free path, and the mean collision time. Okay, so this additional term that you can add, since they will involve positive powers of these lengths and times, they will, by dimensional analysis, necessarily involve more derivatives. Okay, and in fact, the next to leading term, which corresponds to the analog of the dipole, if you want, the next correction, the expansion in powers of the size is the viscosity. Is the effect of viscosity, which consists of two terms. One that is the shear viscosity. You see there is single derivatives. This one has one derivative, which means that this coefficient eta will have to depend, and we will figure out by dimensional analysis on some of this linearly, on some of this time scale or length scale linearly. And then there's another term, which is this. This is the viscosity. Okay, so what you expect? You expect that this term becomes important when you are at sufficiently short time or distances. And let's see that in detail. Okay, so let me just do some very silly dimensional analysis. Okay, what is rho? Rho is the density. Well, rho is controlled by some equation of state, which depends on the detail of the system. But overall, rho will be given by some constant, which is unit of mass density, times some function, which I call rho bar, which I can think of as order one function, at least in the regime where this fluid is almost incompressible. Okay, it compresses itself, but it doesn't change so dramatically. Of course, at a certain point, the fluid can become from gas, can become water, so there can be a transition, but within a certain range, I'll treat it as an order one object. And then you have pressure. Pressure by dimensional analysis is density times velocity squared. So, and this rho bar is just a dimensionless function. Okay, and this is going to be some rho zero, velocity squared. What is the velocity I can think of there? Well, it's going to be, in fact, when you compute when you try to study the fluctuation, you discover that P over rho controls, in fact, P over the rho controls the speed of sound. So this is going to be something like a quantity that you interpret as the speed of sound times some function of order one, which I call P bar. And what about this guy here? Well, this guy here is if you just fix the units, okay, this guy here is essentially pressure with velocity times an additional time derivative. So this is essentially eta. You can write it as rho zero ds squared, which is the same units of pressure, times some time. Okay. To fix the dimensionality here, you have, okay, times some time, which is the time that you can put there. Well, the only time you can think of is the collision time. Okay, so let's play something like that. Okay. So in this situation, now you can ask yourself, under what condition can I treat this? For instance, this one here has a small perturbation, so you can compare these two guys, okay? And you can treat that as a small perturbation where this term is smaller than that. And consider, for instance, a sound wave, okay? So what you have, oh, I can erase this, right? So what you have, let's see if I screw this up, okay? So what you have here, you just have rho, let's say you have something that oscillates. Okay? You are in a situation where you have a sound wave. I'm doing really like what you do when you are, I'm not being rigorous. Okay? I'm just doing what you do when you are drinking coffee and doing an estimate. Okay? So here you have rho, you have 1 over dt. So dt, what is dt? I have a wave, this is going to be some frequency, okay? There's some frequency, and v will be some typical velocity, which gives you the amplitude, how much this sound wave is intense, okay? It's the typical velocity of the wave, and you compare this to this other guy here. This is eta. So what is this k? Well, this is going to be the wavelength of your sound wave, okay, k squared, times the typical amplitude e, okay? Now, the relation between the wavelength and the frequency is given by the speed of sound. So you can write this as eta omega square over the speed of sound square times v. And now you can ask under what situation how this compares to that. Guys, I'm really going to do it. You already see that I'm not a good user of blackboards. Okay. So in the course I give, it took me 15 years to learn how to really write things in the blackboard. Here, I don't think I'll be able to do it in 1 week. So it took me, yeah. Anyway, so this is the thing. So now you start rewriting things that way. So here you have rho 0. Rho bar is of order 1, so this is rho 0 omega b. Bigger or smaller than this other here. This is what? This is rho 0, speed of sound square, tau of collision. Of course, you know where we are going, right? I mean, at the end, it should be, this equation should only have frequencies, okay? So this is this is omega square over v sound square times v. This goes. Get rid of this, get rid of that. Get rid of this, get rid of that, all you get is 1 less or bigger than tau collision times omega. So, the situation where this term, the viscosity term, is a small perturbation of the leading, if you want the monopole term, it's just that you're considering waves that oscillate with a frequency over a time scale that is much, much longer than the time of collisions, okay? During the oscillation of a sound wave, many interactions. Every particle goes very many interactions. Okay? The nature of particles, of individual particles, in that way it doesn't matter. Okay? It's such a slow wave, it's moving so slowly, it's evolving so slowly that it makes sense to aberrate in the motion, in the microscopic motion of the particles. I have a question, okay? So if I say it this way, it looks like this term here. I mean, unless I am considering very pitchy noises, I can forget about it. And that would make mysterious why mathematicians and all people who study real physics study the whole set, which is a perfect fluid plus viscosity, which is just the Navier-Stokes equation, right? These all things in the Navier-Stokes equation. If under the conditions where, if in the conditions where I can use, because remember here I expect there's going to be also higher, I forgot to say, this is the first derivative correction, but there's going to be more. Puff, 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 puff. And you expect very much like it happened here, that, remember here, when we get so close that the first terms in the expansion become comparable, you expect that the expansion breaks down, okay? And here, it seems like that if the higher order term go in the same way, they will be suppressed again by similar powers. And if you're in a situation where the frequency is large enough, then the expansion breaks down. So it looks like in this picture that there is a situation where this dominates, but this is always a small correction. Okay? But actually, that is not the case. There are situations where this is as important as that. But then the other guys you can forget about. And the reason is the peculiar property of the shear mode of the velocity. Because if you look at the, see here, you can decompose the velocity into, it's a vector, you can decompose it into a gradient mode, which is like a compressional mode, and in a transverse mode, which is just a transverse vector, okay? The transverse vector does not get any gradient part at all and Gore because this is a gradient, okay? Essentially, the transverse vector does not have any gradient part in its propagation, okay? At the linearized level, it only comes non-linearly, okay? So then there are situations where actually the leading, if the velocity is small enough, okay, which is precisely what happens when you are in a viscous situation, okay, then this dominates the propagation of the shear. This is why the whole thing. So it's like this, but it's slightly cooler than that. This is why hydrodynamics is a cool thing. By the way, I am not entirely sure if there are situations where the next orders have been considered. Recent years, there have been a system work in defining hydrodynamics in a systematic manner with modern methods of field theory, work by Hong Liu and Rangamani and others, work that we would like to understand better, okay? But do you know if...
Yeah. People who study heavy ion collisions have studied second order derivatives.
Okay. And
in relativistic flow.
And did they need it to match the data?
I don't know, but I think their viewpoint originally was sort of misled by the realization that if you take the relativistic version of this and you just truncate it at first order, you find some sort of acausality. And so they study the second orders as a way to fix that.
Causality is always the case if you work a fixed order in derivatives. It's like saying that you have tachyons, or it's like the same thing, right?
But there is this paper that Sergey and Lam and I have studied at some point, Israel's paper. Yeah, it's a classic paper for second order correction.
I just raised this question to take a little break and let other people speak. Okay, so this is the other example, okay, this is dynamical. But again, these examples are all classical, okay? And again, the same story works also quantum mechanically. And the poster child of this effective description, so this is the effective description in the dynamical classical situation. But again, there are the quantum version and the poster child at the quantum mechanical level without going to the big world of quantum field theory. In the quantum mechanical case is the molecules in the Born-Oppenheimer approximation. Take for instance, this is the standard textbook example of an effective description in quantum mechanics. But again, like in all cases, the possibility of having this description arises for the existence of separation of scale, that you're doing something at long distances compared to the size of the object, that you're considering waves that are long and slow compared to the distances to the collision distance and the collision time, which happen very fast and at very short distances. Again, here, what you have, let's take for instance the hydrogen molecule, you have 2 protons and 2 electrons here, okay? And the main fact here is that the mass of the proton is about 1,000 times to 2,000 times the mass of the electron. So the proton is much heavier, and you're familiar with the fact that something is heavy, it moves slowly, okay? So the time scale of the motion of the protons is much longer than the time scale of the motion of the electrons. You should think of the electron as moving very, very fast inside here, okay? And by the time the protons have moved a little bit, the electrons have gone around with it. So of course, this is quantum mechanical. I'm just trying to give you a picture, a silly sort of classical picture, okay? But that's the idea, okay? So in this situation, what normally is done, okay, to study a system like that, is that you first you work in 2 steps. You first solve the Schrödinger equation for the electrons, treating the position of the 2 protons as fixed parameters. Okay. You solve that, and that will give you, for every position of these 2 protons, the electrons that move fast, they will add up and go to the minimum of the energy, so they will give you a certain energy. Okay, the solution will give you the lowest eigenvalue is a certain energy, which is a function, okay? This energy is a function of the position of the 2 guys, okay? So you interpret this energy as an effective potential between x1 and x2. And in the second step, you solve the Schrödinger equation for the motion of the protons with this effective potential. Now, this effective potential, V, what is the order of magnitude of this effective potential? V, what is the order of magnitude? Well, there's one typical energy scale in atomic physics, that is the binding energy of hydrogen, and this thing should be a function of the x's, and there's a typical length scale that is the Bohr radius, okay, which is therefore x over the Bohr radius, x1 and x2 over the Bohr radius. Now the Bohr radius is simply 1 over m electron alpha, okay? And then now it turns out that another essential feature of this particular case is that the protons not only move slowly, but once you identify the minimum of this potential, they stay very close to there. They don't go around, okay? So there's an additional ingredient to just being slow. They just stay in the same place. Which makes this case slightly more special than what I wanted to say, but this is a detail that we can leave out. In the sense, the fact that they're always in the same point, very close, means that even if they moved fast for some reason, then the electron would see them always at the same point, and you can still treat them in this axis as essentially localized. Okay? But that's a detail. Forget about that. Okay, so you go and expand this around the minimum, and it's a little exercise in dimensional analysis. What you find is that around the minimum, this will give you a harmonic oscillator, and the typical frequency that comes out of that goes like the atomic energy, alpha ME, which is the typical energy or inverse time scale of the motion of the electron, times m electron over m proton. Okay, something like that. Okay, you get, and you call this omega e. Let me call it this way. This is omega e, which is simply m e alpha square. Okay, so again, because of this separation of mass scales that exists in nature, there arises a separation in frequencies, okay, meaning that the electron moves much faster than the proton, and you can view the motion of the protons as the motion of this law object in an average fast-moving electron cloud that adapts to where the protons are. Okay, and actually you can systematize that. Okay, and systematizing this is normally you when you do quantum dynamics you stop at the first stage, which is this, but there are other further corrections that I have not identified written here, and these are precisely like in all these cases. Okay, controlled by the ratio, okay, of the relevant time scale. So omega p over omega e, okay, which is, so this is an expansion parameter. And this parameter is of order me over proton. And if you look at it again, if you revert it, this is this expansion here, which controls that you can do systematically, is controlled. And now if you look in time scales, is tau electron, which is the inverse of the frequency, times tau proton. Okay? So again, it's always an expansion in positive powers of the short time scale that characterizes the fast motion. Okay? So they're all very similar. Okay, and so this is all to tell you that this type of effective descriptions in physics are ubiquitous. Okay? Now I'm hiding here. In the parlance, which many of you, or I mean, I think all of you already know, this way of treating the electron in the quantum mechanical context, this two-step procedure, where you first solve the Schrödinger equation for the fast-moving object, and then you solve for the slow-moving variables. It is also normally referred to as integrating out the electron. Okay, and the reason for that, okay, is just which also gives all this procedure a much cleaner conceptually conceptual picture. The way that this is conceptualized is by the path integral. Okay. Now, physics, mechanics, and quantum mechanics has two, can be described in two alternative but equivalent ways. Okay, mechanics can be described using Lagrangian formalism, the principle of stationary action, or with the Hamiltonian approach. Okay, and the same dualism in description carries over to the quantum mechanical case, where the Hamiltonian approach corresponds to standard canonical Schrödinger equation approach, while the Lagrangian corresponds to the path integral approach to quantum mechanics. And in the path integral, the path integral is beautiful because, I mean, hard and beautiful, okay, often it's difficult to define, but once you buy the concept, in a sense it trivializes physics, because any physical quantity is some correlator of dynamical variables, Q1, Q, tau n. Okay, and the correlator of dynamical variable, everything can be written in terms of correlators on some state, okay, or some different states, okay, and that can always be phrased in terms of a path integral for the functional variables and some action which depends on these variables. Okay, and And as you have learned in school, when you're doing an integral, okay, your slicing space, you can do an integral by summing things this way. If you have to compute the area of this, you can slice like this, or you can slice this way, you can slice it this way. As long as you sum everything, you get the same result, okay? And in some cases, it's convenient to, for instance, in the exercise of analysis, I remember we were always integrating over very complicated regions into dimensions, and there was a clever way of cutting out and dividing these regions into a collection. I don't know whether you guys were doing this in Italy. We were always doing this complicated integrals just to make your life miserable. Okay, and then you have to put them together, and then the question is how to slice it in the clever way. Well, here again, it's a question of slicing integrals. Imagine you, and it works like this, and it exemplifies there. To exemplify what I'm saying there, imagine you are considering a correlator for the motion of the protons inside here, which is a slow motion, okay? But that is a general thing. Imagine you're computing correlators with maybe smearing this time dependence over long times, okay? Which means in a sense that you're only computing the Fourier transform with very low frequency of these variables, okay? You're computing, in other words, you're focusing on slow variables, okay? Well, in that situation, okay, it makes sense to divide your integration variables, Q, into a double set. You can separate it. In fact, the way you separate this thing is arbitrary, and that's the essence, if you want, of renormalization. Okay? There's always an arbitrary way to slice, but you essentially divide your variable into two groups, the slow ones and the fast ones, okay? Corresponding to the variables. Let's say you work in Fourier space, functions can always be used in coordinate, which in this case in quantum mechanics is just time, or Fourier space, and you separate them, they are the fast and the slow. And if you're only interested in the slow variables, then it makes sense to perform this integral in a double step where this measure is now the product of the measure of the slow variables and the fast variables. This is very sketchy, but I cannot do it better than that. Okay, of course, there's a whole world of complication in how you do this slicing, but the concept, I think, it's very simple. And then you do these integrals. Okay, now you have your action is a function of the slow and the fast. And okay, you do the integral first, and of course this integral can always be written again as dq slow, and of some other expression. In some cases, this expression may not even be real, but over broad conditions, which I can tell you in a moment, it will be real. So this is some effective expression that depends only on the slope. Okay? You're not doing anything. You're writing something very general. Okay? This is some other function, okay, that you obtain by integrating out. And now, what is essential, so this function could be whatever you want. It could be very complicated, it could be imaginary, you will have whatever you want. Okay? So in principle, this operation here doesn't mean anything. What is really important, however, is that when these are fast and these are slow, okay, then very much like in all these cases, the time scale that controls the slow variables will appear in the numerator, like in all these cases, okay? And which means that the effective action that you obtain here has this short time scale in the numerator, and to match the dimension, every further power of this short time scale will come with a time derivative, okay? So in other words, what you will have here is a Lagrangian that writes in terms of a derivative expansion, okay? And precisely associated with the fact that this time scale is very tiny compared to the long time scale you're considering, physics at those time scales, I mean, will not give rise to any non-locality in time. If you want, that's a measure of the fact that if these variables are slow, this derivative expansion is convergent, okay? In other words, this is a local action, and it's a derivative expansion. Again, it's a derivative expansion like in all the cases, okay? And the slower these variables will be, the more convergent this expansion, okay? And so this is just to tell you that effective distance description are ubiquitous. I already said it. In fact, you can understand from this that their very existence, in a sense, is why we can do physics. Okay, imagine a situation where, like here, there is charge everywhere. It's messed up at every moment we move around. There's no situation where we can go far and say, oh, look, now things look simple. It's going to be a mess all over the place. Okay, it's precisely the separation of scales that gives physics its character compared to other disciplines. In a sense, chemistry and biology are precisely the way they are because they deal with situations where you have a lot of complexity at the scale where you're considering, okay? At the scale of the atom, the molecules, at the scale of the cell. You cannot step back and look at things from far away, okay? You are there, you are inside there. And it happens that, for reasons that we don't understand, there are 10 to the 60 orders of magnitude between the Planck length and the Hubble scale, and this gives plenty of space for situations where you have separation of scales to make physics a possible science. This is why, in a sense, we exist. It's because of separation of scales. Okay? In this perspective, quantum field theory is, in the model view of quantum field theory, is that quantum field theory is yet another iteration of the same stuff. Okay, the reason why we can use quantum field theory is because nature has handed us situations where there are separation of scales, and we can write Lagrangians, effective Lagrangians, for quantum field theories, like this one here, where the expansion is convergent. It's convergent because there seems to exist a separation of scale. Okay? In some cases, we know it exists. In other cases, as you will see in the course of these lectures, it's more. I mean, we have to speculate to infer that. Now, I should say that I am old enough. In fact, I'm old. And I was saying here, I'm saying, oh, some time ago, now it turns out it's 4 decades ago, when they started doing physics in the 80s, certainly in Europe. And in fact, there are still pockets now where there was this notion that quantum field theory is different. Quantum field theory is the thing. Okay? Quantum field theory should be, it has some stronger consistency constraints, and in particular, one of these constraints is that it should be renormalizable. Okay, if it's not renormalizable, then we cannot make prediction, and if we cannot make prediction, then it doesn't make sense. So it has to be renormalizable. Okay, I mean, biology is not described by renormalizable Lagrangians, and that's the situation. We cannot argue that way. So anyway, this view that quantum field theory was special was dismantled in the 60s and 70s, largely by Wilson, with his understanding of truly the meaning of what, he basically understood what is quantum field theory, and then this was applied and made canonical in several ways, in particular by Weinberg. Okay? So So the modern view, which I will now present and talk about, is that also quantum field theory is just the same story as we have here. 'Should we take a little break? 10 minutes, just 10 minutes, okay? Okay.
Welcome. What's up, John? Are you guys still closed? Yeah. So is this going to be here all week, or so the initial plan was 2 days here and then move uptown as soon as possible. But I still have one. Yeah. Sounds pretty well.
Question of fluids, information why this doesn't work. Because in other words, we can say why it's important because of turbulence, right? Because there is over long time takes kind of energy out of your slow moves and fast moves.
I'm glad you're all here.
Something works.
I guess we're interesting out here, but not like uptown, I guess.
I guess when I got to past like summer, so I don't know, like,
You're expected to work more summer.
yeah, it's kind of crazy, right?
Yeah, we're discussing whether to have a vote of no confidence. All that's happening,
Revolution.
and the area where they had the tanks is still blocked off. It's right in front of my apartment. So I still have to walk for, my walk is still longer than my work because of my normal walk is through where the
So the behavior is turbulent.
But it's much less dangerous.
Yeah, you can provide, but this curve, they provide kind of boundary condition.
Yeah.
But I would say even without this term, I have a question, but at least that's my understanding. So that's how people usually get the whole strategy.
No, these are around here.
Can you suggest surface condos for interesting? You know,
For instance,
I'll go explore a little bit. You'll have me.
all these new ideas
May I want to come?
going beyond the classic.
Oh, yeah. Or incompressible,
I have one that I never finished, so I should finish that. Yeah, read. I don't know about give out, but
No, I'm not
just want to read.
Yeah.
Okay, yeah. Then I can say I taught a couple of years ago at Les Uches, and they required that we do a review, and then I never ended up submitting it to archive, which they were angry at me for. Because the archive just like needed figures and like more edit. It needs like a week of time that I just didn't have. But they wanted something. So basically, I have a draft that was like the minimum thing. So there might be mistakes, but at least it's like a snapshot as of 2021. Has a couple of years to come. Yeah, I can send that to you. In fact, if you look at it and you have comments, that would be here. At some point, I still have the goal of putting it on the archive.
You should.
Yeah, but now I passed they already published it in Signpost, that the people who were good citizens. So nobody's bothering me anymore, so it's not clear. It's not clear this will ever happen.
And you just, you
Oh,
piece of paper,
fine.
this piece of paper,
I'll do that. Yeah. Since you printed it, I'll actually read these.
Thanks.
as a review, no, it's only about production. It's only production because it was a school that was all about dark matter. So I was only lecturing on production. It was only production.
And if I won, review on very small.
That's a good question.
You should recommend.
No, we should ask Ken. Ken would be the person I would ask. He's an expert. So, but I don't know. Oh, okay, like GeV scale electrons. Yeah, there's things by like Tongyan that are probably good. Yeah, sorry, I was thinking more the axion. That would be what Ken would know. And dark photon. Okay, you mean for yeah, like GeV scale electron scattering. Then I don't know how good it is, but I know that Tongyan has a review. So I'll send you.
That would be right.
I'll send you a review, but I haven't read it, so it's not a. But I'm not sure. Or Reuven or Tomer is it people so trust. Yeah, I know Tongyan gave Rattazzi lectures, but let's see. Where are you lecturing? Yeah, I know she has a review and she works on that. It's pretty old now.
I didn't read it.
It's pretty rapidly developing.
Yeah, thank you. Yeah. I was thinking I can get it.
Yeah, well,
It's pretty broad.
like even if
Next to you, there were 2 slots.
yeah, well, next there were in theory 2 spots, but the chosen.
At least she's somebody who works on this. She wrote a Rattazzi lecture.
Oh, so
But
you
it looks like it's
no lady.
I usually want. But yeah, it looks like dark protection.
Okay. I found the spot.
Yeah. So there's parts A and B.
Well, you invented it.
Yes.
It's an effective spot. It's not a
I'm not
official
officially
spot,
tagged, so.
but if you just keep it close to
Yeah, that's a good thing. Yeah. Okay, so I'll send you my draft and then I'll let you know if I find anything else.
It was like the lost. Or like technical. This is relevant to, you're not too high. Too more.
No, I was doing the No, so the algebraic object is what's called a fusion. Yeah, so you have like so Santa Cruz, you have like all the objects. Simple objects, and if you multiply them together, you'll generate a linear combination of other things rather than just one other thing. And then you can't necessarily take those. You can subtract, which is what they call non-movable symmetries. Yeah. So then,
Oh, it was okay. My kid was in a math competition.
so like in FCNC, right, you have the obviously have right, that does not. And then you have spins.
So yeah, so you're all set. You can tell me everything this week.
Yeah, I got something to say.
Okay.
Yeah.
So we just pick one of these days after this.
Yes.
Squareness identity plus the spin flip defect. So this is actually so the IC.
What is gauge?
So you like you can think of it like mono-type symmetry. So you can actually in seeing the non-renormalizable symmetry is composite, so you can actually engage
So at a certain point, maybe around 12:30 behind. Okay. Okay, so let's now let me now apply the same perspective in quantum field theory. So the idea is that very much like everything else, quantum field theory in all its incarnation, and at the end, of course, we're talking about the standard model, but in all its incarnation, and that's certainly the case for quantum field theories that are used in condensed matter physics, but that's also the case in the quantum field theories that are used to describe energy QST, the lagrangian of particles. All these cases, very much like everything else, are effective field theories, okay? In other words, all description, quantum field theory description, will be, is. Okay? That's the ideology. Every quantum field theory is an effective description, valid up to some timescale tau, some length scale L, but okay, we are in relativistic physics, there's only one thing, it's L, is the same thing as tau, okay, measure things this way, and physics, I mean, the Lagrangian, very much like in the case I was describing before, by integrating out the fast variables, the Lagrangian will be written as an expansion in positive powers of some fundamental length scale, which by dimensional analysis we can write as an inverse of an energy scale, which is like all this fundamental scale, like the mean-free path, the mean-free time, the size of the distribution, the frequency of motion of the electron, which is a microscopic length scale with some very specific physical meaning. It's not an artifact. Because normally when you do quantum field theory, you see lambda, oh, lambda is the cutoff, we're normalized. For me, lambda is the physical scale, like all. I'm just saying quantum field theory, of course there is there are all layers of complications, technical complications in quantum field theory that make the physics fuzzier. There's a fog of technical complexity. What I'm trying to insist here is that yeah, I mean, behind all these technicalities, it's just the same business. It's the same business that we had before. Okay, expansion. Very good. So with this provision, let me give you the example of what I mean, okay, and how it works, okay. In the case of let me consider the simplest possible case, which is a field theory of a single scalar field, phi. And just to simplify the discussion at this stage, let me also assume that there is a symmetry phi goes to minus phi. Okay, just to simplify. For some reason there is this symmetry, but in a moment I will drop it. But let me. And now the rule now is that given this physical scale lambda, I very much like with the multiple expansion, like in this distribution I had before, when you're far away, okay, for a generic distribution here, you will have all multiples. So in general, the physics at long distance is described, okay, if you had infinite accuracy, by an infinite set of multiples in an expansion in positive power of the size A. And here, the modern perspective is the same, is that the Lagrangian, which is the physical object, here the physical object was the potential, here's the Lagrangian. The Lagrangian is written as an expansion in positive power of the length, which is to say inverse powers of lambda. So now, on top of that, let's assume that there exists a decent vacuum, okay, around which we expand. And let me, without loss of generality, you can always take that vacuum to be at phi equals 0. So your around the point, the expansion should make sense. So the expansion should be analytic around phi equals 0. So the Lagrangian is a polynomial in phi. It's a polynomial in derivative because of locality, because we integrate our short distance physics very much as I was discussing before. Okay. So the Lagrangian will be something like this. Start with the kinetic term of the field. Then there will be some mass term field. And there is some, let me use the same notation I have here. Let's say, some. I will not be very careful with signs and factors. I'm very, very schematic here. But then there are, and these terms, this coefficient, the field phi as dimension 1, the derivative as dimension 1, and that fixes the dimensional coefficient, given that the Lagrangian must have dimension 4, has dimension 4, okay? Because the integral of the Lagrangian is the action, and the action is dimensionless. So you have this, but then you have all other terms that count with more fields and more derivatives. So this object here consists in terms in the Lagrangian that have positive or 0 powers of the scale. Okay, lambda 4 is dimensionless, and I should write here something that goes like lambda, but for the moment let me treat it as a separate parameter, and I will explain this better in a moment. Okay. And then you write everything very much as we were doing before. So what do you have? At the next order, you can start having terms that have 6 powers of the field. Okay, the dimension here now, the 4 requires a power of lambda times some coefficient, which I call lambda 6. Okay, some numerical coefficient I call lambda 6. At the same dimension, there will be a term which I call eta 4, which is something which involves 4 powers of the field and 2 derivatives. Again, it has the same dimensionality. And you can have more legs, but no, that's basically ends it. And then you can go forward, you can go to next order, you have lambda 8, 5 to the 8, lambda to the 4th, and then you have some, let me call it this, how do we call this? I don't know whether I call this eta 6. Let me call it eta 6 phi square over lambda to the 4th, and so on. So this is 1 over lambda square, and this is 1 over lambda to the 4th. And the more you go, the more terms you can have, the more permutations. So this is an infinite tower of terms that are expected to be there. Okay. Now, a few comments. If I interpret this lambda as the physical scale, I will argue a bit later, maybe if I have the time. It turns out that this coefficient cannot be much bigger than order 1. In the sense, these have to be order 1. I will explain in a moment why that has to be the case. In a sense, well, let me say, if this coefficient were to be bigger than order 1, where order 1 should be specified slightly better, then the expansion would break down at this expansion, when you compute physical observable, will break down at length scales that are shorter than lambda. They're longer than lambda. In that sense, therefore, it violates our assumption that lambda is the scale where this description breaks down. Very much like for the fluid or for the multiple expansion. My lambda is truly the physical scale, is very much like here. Is the scale which is like the size here. When I get at that length, the expansion breaks down. Okay? And quantum mechanical consistency in a sense here tells you that if you want to interpret lambda that way, this coefficient, this numerical coefficient cannot be bigger than suitably defined order 1. Okay? So for the sake of this discussion, you can think of them as finite quantities of order 1. Okay? Now, here I've treated this, so as I said, as I emphasized here, the possibility of deriving and using effective descriptions is contingent to the existence of a separation of scale. If you're not doing things from far away compared to the scale of microphysics, then you're stuck with an infinite number of parameters. So we have somehow to insert here this fact, okay, the fact that we can do physics at distances that are much longer than the fundamental length scale or the inverse energy scale. And the only way to achieve that is to allow the quanta of this theory to be light. Okay? In other words, for some reason, which we may or may not fully understand, I assume that this m is much, much smaller than lambda. In a sense, this m, even though it's a parameter in the theory, is the analog of 1 over r here. Okay, when you are, it's the parameter that controls the existence of a separation of scale. In this case, it's the position of the observer, so that's a piece of cake. Okay, in this case, it's the very parameter. Yeah. But you see, even here, if there was a wall here, then you cannot go further than something. For some reason, the problem may have some constraint that does not allow you to go too far away.
So why would M be more the analog of like the A in the multiple expansion?
No, the analog of A is this. A is the size, is the length scale where you discover the truth.
Yeah.
Or you know what things are.
Yes, yeah.
Okay, is the microphysics scale. Is this clear?
Yes.
Of course, yeah, of course, the very different situation right here. This is a quantum field theory, this is a multiple expansion, but actually, deep inside is the same situation where you're far away, you're looking at somebody, looks like a point, okay? Then you look better, it looks like, and then you describe the position of the guy just with the point. Okay? Similar, by the way, yeah, I should have said that another beautiful example where this effective description arises is celestial mechanics, okay? Where even though the Earth is a huge object, the Sun is huge, this Jupiter is big, is fluffy, Saturn has the rings going around, there's moons, the other guy has a strange shape. They're all so far away that you can treat them in first approximation as point, which is the equivalent of the monopole approximation. Okay? And then you can go on. Yeah, same situation, okay? Different system. So this is the way to think of quantum field theory, and the ingredient with which we meant this is just dimensional analysis, locality, and the fact that we are trying to insert into this system the same notion we have learned before. Okay, there is a length scale that controls the complexity of the system. Okay, and positive power of the length scale should control the expansion in the qualities of the system. Okay, so this coefficient, which is infinitely many of them, define what this system is. Okay, but in order to, very much like in all the other cases, and as it will be clarified in a moment, in order to see all the structure, you have to go to do experiment at very short distances, which is to say at high energy. And the way to see that, let's see that explicitly, let's start considering computation of some scattering amplitudes, okay? And as I said, this is a meta course. It's squiggly throughout, okay? Normally when you do Feynman diagrams, if you don't compute things properly, then you get D, okay? Here I'm getting less than D. I'm just writing everything. It's just momentum I indicate by E. I do not pay attention at how Lorentz contractions are made. I don't write about it. It's purely squiggly qualitative, but again, because I'm aiming only at one thing. If you're far away, then you need little information to study a system, to study a dynamical system whose microdynamics happens at very short distance. And in the case of quantum field theory, or what means going to long distance means doing scattering with particles that have very long wavelengths. Okay, that's the relevant distance, and so which means that you're going to low energy. So in this particular case, let's consider. So therefore, with that view, once you buy this, okay, once you buy this, it means that there exists a regime where the energy, and this will be crucial in all the discussions, is much, much less than lambda and much, much bigger than m, okay? In this regime of energy, I can treat this field as essentially massless, and in what I'm discussing now, I can neglect the mass, okay, we neglect it in my squiggly computation. Okay. So let me qualitatively estimate, let me not say compute, estimate a few quantities. Compute, for instance, the 2 to 2 scattering amplitude, okay? So just take this Lagrangian, and you go ahead, and you have, this is the leading contribution, this is input. This is the first diagram, just given simply by this term. But then there is another term. See, this guy has 4 legs. So let me write. So this is lambda 4. And then there is a diagram coming from there, which has eta 4. And let me indicate it with a bigger interaction vertex, meaning that here there are 2 derivatives, means that this comes with 2 powers of energy. So the corresponding amplitude will go like lambda 4 plus what? Well, eta 4, 1 over lambda square, okay? And the momentum will give you 2 powers of energy. So essentially something like this, okay? And of course, I could have gone on and looked at terms like here that have, I don't know, like this one here, which have 4 legs, and it could even be another term like here, which I indicate like this, and this is plus eta 6 e to the 4th lambda to the 4th, okay? And more terms. So what is the deal about this? Well, the deal, again, is the same as, again, we found before. Your amplitude is written as a virtually infinite polynomial, but in positive powers of e over lambda. Now, these coefficients, they may be large. In fact, they cannot be bigger than order 1 in a way that I will specify. So they're just finite quantities. So that means that if you can buy yourself to go at sufficiently low energies, okay, and given the precision of your experiment, imagine your precision of your experiment is I don't know, 1 per mil, and you can go to energy that are a factor of 100 less than lambda, then this you will not be able to see. Okay? Same situation. At fixed accuracy, there's only one term that survives, and it is this one. Okay? It's very much like in all other cases. And now, if you increase your accuracy, working at low energy, you may start seeing this. If you increase further your accuracy, you start seeing that. And so on and so forth. Of course, the alternative to see these other guys is to, rather than increase your accuracy to have a more precise detector, is to just increase the energy, which is the same as in the case of the multiple getting closer to the distribution. Okay? So there are can either do experiments staying here by being more precise, or go to shorter distances. And in particle physics, going to shorter distances means scattering quanta that have shorter wavelengths, which those prove the dynamics at shorter distances. Okay? But on the other hand, if you are allowed to go at very, very low energy, everything reduces to just this. Well, that is 4 to 2 to 2. What about, I don't know, 2 to 4? Okay, let's consider another process. Okay, so let's say I've measured 2 to 2, okay, and I've extracted the value of lambda 4. Am I in business? This is very much like here. Let's say I've done a measurement. I've done several measurements. In some reason, it looks like you've been able to measure Q0. Is that enough to compute the field elsewhere? Here you can do the same thing, right? I've done this experiment, I've measured this. Is that enough to predict other quantities, in particular the 2 to 4? Okay, so very analogous. Okay, so what do you have there? Okay, let's now compute. Look at the Feynman diagrams. You have this, 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 and this. Okay, this is you now to have 2 to 4. You have to iterate is lambda 4, lambda 4. Okay, there are 2 vertices with lambda 4. Okay, now you also have the phi to the 6th. Okay, you can have this other vertex. And of course, I'm a complete moron because now I cannot go. Sorry, guys. Let me go further up so that I can write. So, okay, 6. And more, right? There is again, you can do this with lambda 4, and here you can put eta 4. Okay? You can put this other vertex, you can put even, sorry, this is the tiny vertex, lambda 4. You can do also the square vertex, okay? Which is that okay. Which has 4 inverse power of lambda. And let's power count how these terms behave. Okay, here, what we have here is lambda to the 4 square, but we have a propagator. So this is lambda to the 4 square, 1 over e square. The reason why here we get an inverse power of e, here we don't, is simply because of the normalization of states that we are using. Okay, it doesn't have any impact other than that. What matters is looking at the relative behavior with energy of the various terms. And now, if you look at this other term here, this is simply lambda 6 over lambda square. Okay, there's no power of energy, it's just this vertex here. There's no derivatives. And then there are these terms. You have a propagator here, which is an inverse power of energy, but you have 2 derivatives there. So at the end of the day, there's no power of overall homogeneous power of energy that remains. Okay, this is something that scales when you scale the energy as e to the 0. So this goes like lambda 4, eta 4, but eta 4 is a 1 over lambda square, so and so on and so forth. Okay, so at the end of the day, you can factor out an e 1 over e square, and you have the same situation. You have, as you had before, you have lambda 4 square plus lambda 6 e square over lambda square plus lambda 4 eta 4 square and higher power. So again, it's the same stuff. Okay, at higher energies, at fixed precision, more and more terms become important. When you go to sufficient, if you can go sufficiently low energy at a certain point, this will go below your precision, you will not see them, and everything is predicted in terms of the thing that you already measured, And means that in this sense, very much like in this case, you have a predictive theory. Okay? In other words, you work in a situation where the energy is so low that basically all these other terms are negligible, whatever you compute, compare to this one. Okay? And of course, if you go to even lower energies, at a certain point you will realize that your field, the field that you scatter, are actually massive. It's very much like what happened with neutrinos. Okay? In all experiments, they are so light that it took decades to infer that they had a mass. Okay? So if something is very light, you need a very precise experiment to infer the presence of its mass. But in this case, okay, you go sufficiently low energy and you will start seeing that the dispersion relation of this particle changes. Okay? But again, these amounts going to even lower energies, it will not impact. Okay? If you go to even further scale, at a certain point when the energy will be over the m, this term will become important. Okay? There is a mass, but by then, these guys are all gone. Okay? Again, unless you have a very, 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 very precise experiment that can pick up all of them. I mean, a few of them. Okay? But anyway, at finite precision, you will only be able to access a finite number of them. But there is a specific limit, okay, when you send E over lambda to 0, where really all these guys disappear, and this corresponds formally to the limit where lambda, if you keep E fixed, where lambda is set to infinity, or in other words, the limit where the microphysics scale of this system is becoming infinitesimally small. Okay? And in this situation, you have that your Lagrangian reduces to just the first terms, those who are not suppressed by an inverse power of lambda. And you already recognize how this Lagrangian is characterized verbally as compared to this, to the one that we started with. This is the one that in a class you call the renormalizable Lagrangian. But I haven't discussed anything, I haven't discussed loops, and I will comment in a moment on that. But this comes even before doing loops and doing anything like that. Okay, so just by doing this very simple-minded computation, you realize that the famous renormalizable Lagrangian is nothing but what is left if you're allowed a sufficiently large separation of scales. Okay, so in other words, given a large separation of scales, any situation, even the most general one, will boil down, will be described by renormalizable Lagrangian. So the relevance of renormalizable Lagrangians is just an unavoidable emergence. Okay, it's something that emerges in quantum field theory whenever you're allowed, whenever there exists a big separation of scales. Okay, and so when there is a separation of scale, any Lagrangian sufficient low energy will look like a normalizable one. And of course, that implies that, based on this logic, that you can compute Higgs in terms of few parameters, which is what in the old days was called the famous predictability, predictivity. But in this case, it's not asked as a principle. It emerges as a physical property, consequence of some physical parameter choice. A parameter choice where the mass scale that controls the minimal frequency of your quanta is, for some reason, much smaller than the microphysics scale. Okay? Which is, again, the recurring theme of this discussion. Now, this situation, which I discussed here for a simple theory of a scalar field, is clearly, obviously, valid for any other construction involving gauge fields, fermions, okay? And the basic story is that, if you want, is that the basic story is that your Lagrangian will be written as the sum of some operators, okay, where these OI now mean all those terms with scalars, derivatives. Now you can put in gauge fields, you can put fermions, whatever you want, okay? And we learn the logic, okay? The Lagrangian is dimension 4. These operators are monomials in derivatives and fields, so they start at some finite dimension, 2 perhaps, like the scalar mass, and they can go up to arbitrary large dimension by adding derivatives in lengths, okay? And so the Lagrangian is dimension 4, so given the dimension of this operator I, this GI have dimension 4 minus the dimension of this operator, okay, where delta is the dimension. Okay, and now, whatever you compute, okay, whenever you perform an expansion, the expansion parameter will always be a dimensionless quantity. So if you're at energy E, again, very much like we did before, all amplitudes, all observable will be written as an expansion in powers of E times these couplings, and by dimensional analysis, the effect of this coupling is controlled by their dimension, as we did there, and you will have something like E to the delta I times 4, okay? So that means that at energy E, the relevance or irrelevance of any coupling is controlled by this combination, which I call G bar, and which is a dimensionless quantity that controls how important or unimportant is this coupling at that scale. Okay? And now, based on the dimension of delta I, you can identify essentially three situations. Okay? You have the situation where delta I is bigger than 4, okay, which is the case of all the tower of operators that I raised here, okay, all the operators with more derivatives and more fields, for these couplings become, given this power is positive, become, if you're given the possibility of having a separation scale that E can become small enough, then these guys become negligible at sufficient low energy. And couplings like these are called irrelevant. Meaning that these are the couplings whose impact at low energy disappears. Notice that there's an infinite set of these couplings, okay? And these are precisely all the couplings that characterize this non-renormalizable interaction, if you want. But at low energy, they disappear, okay? And then there are the couplings that have dimension strictly less than 4. And these couplings, like the mass, take for instance the mass square, the impact of the mass in the computation at high energy is measured by the mass divided by the energy square. If you want, the inverse, if you want, is 1 over the inverse of the gamma factor, or the boost gamma factor of this quantum, right? Very, very boosted. Exactly, the boost factor is, you can expand the inverse powers of the boost factor, okay? The limit where the mass goes to 0, the boost factor goes to infinity. And again, so these couplings, if anything, become important at very low energy. In the case of this expansion, there's not a real analog, okay? Maybe imagine perhaps that there is a mass for the photon, and somehow the real potential is not this one, but there is some exponential decay very far away, and you have to go very far away to see that. That's not contemplated here in this situation. And it's interesting to see in the case of the fluid where an analog infrared scale like this exists. Anyway, couplings of this type, they become important at low energy, in the infrared, and become unimportant high energy, are called relevant. The word relevant to irrelevant is just based on the fact that normally we measure things at low energy, okay? Going to energy is more expensive. We are stuck at long distances, so these are relevant, while these ones become only important if you have sufficient probing power to go to high energy. And then there are couplings that, at least in first approximation, where delta is dimension 4, and for this one, at least at this naive level of description, their importance is independent of the scale. They're essentially important on scale, and essentially they are the transition between these two regimes, and these are called matching. And these are essentially the couplings you're most familiar with when studying beta functions and physics in particle physics. Okay. Very good. So now I should say this in words, and so you will tell me, well, I've done quantum field theory, you're a fake, you made things very simple. In reality, things are more complicated because you have to compute loops, okay? Quantum field theory is not fun if you don't compute loops, and until you have computed the one loop, you cannot say that you have understood quantum field theory or even started understanding it. Now, it turns out that what I just told you, the picture I just gave you, in fact, also carries through when you consider loops. Okay, and there are various ways to understand that. At first sight, you may worry that loops screw up. I think I need to go fast on this. At first sight, you may think that loops can screw up things because, let me give you an example. Okay. First sight, you may think they screw up things because, take for instance the 2-to-2 amplitude, okay, which at first order is given by lambda 4, okay, as I said, and then I mentioned, all these other terms are negligible. But then somebody can say, well, look, there is this other term, lambda 6, but if I close a loop here, and this will have 4 legs. Okay, so while this is giving me a term, a contribution to amplitude goes like lambda 4, this will go like lambda 6. There's 1 over lambda squared, remember, is 6 legs, so it has an inverse power of lambda. But now you have to consider this loop. Okay, and this loop is quadratically divergent. Now, the idea, okay, is that our effective Lagrangian, very much like here, is coming from having integrating out all the fast modes. So in other words, when I compute quantum fluctuation, which is today, when I do my path integral, I must cut off somehow this integral, and the cutoff of this integral will be somewhere around the scale lambda, which is the one that separates the fast modes from the slow modes. Okay? But even in that case, what you have is that this diagram, okay, this seemingly meaningless integral, however, computed with this qualitative but physical perspective, gives you a result where the inverse power of lambda is compensated by positive power of lambda there. So you get effective amplitude is lambda 4 plus lambda 6, and there's going to be something like 1 over 16 pi squared, something like lambda squared over lambda squared, okay, and goes away. Okay? So you get indeed that no matter how soft the energies of these legs, okay, the legs that close onto loops can be very very energetic. Okay, this P going through this loop can be very, very large, and the largeness of this momentum can undo the 1 over lambda suppression. Okay. Now, why is this not an issue? Well, this is not an issue because if you look at what this does, it just redefines what lambda 4 is. Okay. At the end of the day, if I were now to do the same computation, which I stupidly erased, okay, of the 2 to 6, the way lambda 4 and lambda 6 appear, okay, is precisely in the same combination. So if I call this lambda 4 prime, the formula will be the same. So in a sense, the real quantity that defines the long distance physics is not lambda 4, but this combination. And you can go on and on and on. Okay? And so in other words, this result is true also when including loop up to what we call schema definition or redefinition of your coupling. But it's true that at the end of the day, it's always true at the end of the day, if you go to low energy, there's only one combination of coupling that matters, and that enters precisely in the way lambda 4, the way we figured out with our silly first computation. Now, it seems like this, it's a bit ugly to do things this way. There is a very straightforward approach to make this automatic, and that is the use of dimensional regularization. What is dimensional regularization? Well, if you want, one way to implement this is to simply say that, look, phi to the 6, when I write phi to the 6 in the Lagrangian, I'm not really meaning phi to the 6. I mean phi to the 6 minus the effect of this loop. Very roughly, okay, p square phi to the 4. In such a way that, so this I call phi to the 6, suitably defined. Okay? If I write the Lagrangian in terms of objects that have many legs and you subtract all these potential divergences, essentially you reshuffle the definition of your operators. At the end, you get back to the naive picture I had before. And there is an automatic way of enforcing this definition of operators is the use of dimensional regularization. And the practical reason for that is that in dimensional regularization, and why it's possible is because it's equivalent to doing this definition, all power divergences are absent by construction, okay? But it simply amounts to that, okay? So in this respect, loops are not an issue, okay? And now this fact, the fact that you can do the procedure of renormalization in this systematic way, even for Lagrangians that do not appear renormalizable, became clear to people in the late 70s. And references for that, I mean, maybe I can give you some references. Weinberg has written a crucial paper entitled Effective Gauge Theories, where the advantage of the user of dimensional regularization was pointed out. This thing about the fact that only specific combination at the end of the day matter is essentially big. This is the poor man description of that essence of the paper by Polchinski on the Wilsonian normalization group. Okay. Oh, this is very sketchy, 2-minute explanation. Okay, and now it is the standard perspective. Okay. So, in conclusion, the point here is that at any, in view of this picture, given the possibility of the existence of separation of scales, at low energy, any quantum field theory behaves like a renormalizable one. Okay, so normalizability, if you do an experiment and your Lagrangian looks normalizable, you say, haha, that means, okay? It's not that the good Lord has given us a phenomenological Lagrangian so that we can make prediction. So the good Lord has given us a separation of scale such that at the scale at which we're making experiments, we are only accessing these few parameters that correspond to the renormalizable. So this is the modern perspective on, and in this respect, okay, you can say that the couplings that appear in the renormalizable Lagrangian are the analog of, if you want, define elementary particles, okay? Those that characterize the particles in the limit where you send the scale lambda to infinity, okay? Where the structure of the underlying theory is central arbitrary short distance, and the particle essentially become elementary. And while all this higher dimension operator, this infinite tower, describes, in a sense, the structure, okay? What this this elementary, this particle that are essentially points, okay? But points in the sense, a point particle is described by a renormalizable Lagrangian. So a point particle is described by a few coefficients that are determined by the operator given that field, the field that you have in the theory at dimension less or equal to 4, and all the other terms can be viewed as the microscopic structure. Now, maybe to, I don't know whether I can make it till the end by should I try and I have 20 minutes, right? No, the transparencies are too complicated. Look, let me take the risk of not finishing, okay? At least today I will do it this way, okay? I want to tell you something about, there are two things that I want to tell you to conclude this discussion, okay? The first thing is that, no, I think it's more important to forget. So I want to tell you something about about why these couplings cannot be bigger than a certain amount. Okay. So in other words, what you can prove is the following. Let me just make the statement. Imagine you've written your Lagrangian in the following way. d phi, let's stick to the scalar, okay? And then write all the interactions. The interaction will have, and you can distribute the derivative as you wish. There's going to be L derivatives, n power of phi, okay? And there's going to be some coefficient C and L, and there's going to be a power of the scale, which is L plus n minus 4, okay? And now the question is, what values of C and L are allowed, okay? And how can we address this question? Well, we can address this question only on the basis of our hypothesis. And if you don't make an hypothesis, then you cannot make a question. So the hypothesis is that lambda is truly a physical scale. Okay? The hypothesis is lambda is truly the scale where the expansion breaks down, okay? Which means, by definition, that as soon as you go to energy that are a bit below lambda, let's say a factor of 10 less than lambda, the expansion starts to converge, and you start getting less and less terms relevant in your computations, right? in the computation of your quantity. In a sense, that means that your scale lambda is truly like this distance here. As soon as you go, if this has length 1 centimeter, as soon as you go 3 or 10 centimeters, this expansion starts working. Okay? Now it turns out that if that is the case, then when you compute loops with these interactions, you should not get, if these C are too large, you get lots of power of energy. If these are too large, you get a situation where the expansion breaks down at energies that are lower than that, okay? And there is an absolute upper bound that you can infer very quickly. If you want, I can show you, if any of you is interested. It's a very quick argument, which allow you to infer what is the upper bound on this CH. And what you find, the CH should be less than essentially order 1, but more precisely powers of 4 pi, because in the loops you have these 4 pi's that come from the integration over momenta. I'll tell you in a moment. So, and this is the following power. Okay, essentially, and less than that. If sum of DCL is way bigger than that, of course, this is very qualitative, is way bigger than that, then in some of your computations, something becomes, there's going to be an infinite series of terms that become important at energies that are below this. So I can show you later. And notice that when you're familiar from electrodynamics, then if you have a coupling, you call this E. If you have 4 legs, this is E squared. If you now compute a diagram where you exchange a photon, another photon emit is E cubed. So the number of, if you define some, you can define a fundamental coupling if you want, and measure this, the vertices here in terms, let's say that these now are, let me call these guys C and L tilde, and put here some coupling to the n minus 2. Okay, you have n legs. Remember, if you have 3 legs, E squared, E cubed. Okay, you write something like that. Then the statement, the statement here, okay, C and L originally equal C and L tilde G star to the n minus 2. This is less than 4 pi n minus 2. So if you interpret this as order 1 coefficient, you have that the coupling should be less than 4 pi. And so this property that in any effective Lagrangian, the couplings that control, the coefficients that control the higher order terms satisfy roughly a constraint like this, is not known as the eighth-dimensional analysis, or NDA. It's something that normally you wouldn't care so much if you only, if you want to be, if you have a gross attitude. But in situation where you want to try to be slightly more clever on assessing this coefficient, is actually quite useful. Remember that if in a concrete situation, this coefficient will control e to some power g star g, a coefficient, which I call g star, to some power over lambda, and knowing, having an access to how big can g star be is important experimentally, okay? Increasing the energy by a factor of 2 costs a lot of energy, okay, costs a lot of money, sorry, and energy if you want. And so being able to assess this coefficient in a slightly more accurate way is important. This approach has been viewed in the years as some crap done by phenomenologists. Even some very respected physicists presented this as the stupid way of treating 4 pi as infinite. This is not the way. This is simply a way of normalizing things in the most convenient way. If you want, this amounts to the fact that the usual normalization h equals c equal 1 is not the most convenient one to do computation. The most convenient one is h bar over 16 pi squared. This is a much more convenient set of units. In these units, the E in the E that appears in the electrodynamic Lagrangian is E over 4 pi, is E hat, and that's precisely the expansion parameter of groups. Okay, so that you don't you get. And now, of course, you can say that in a limit where E is 10 to the minus 100 millions, you don't give a damn. That's not the case. Okay, so it's. And it's interesting that this property.
E only square in that problem. E over 4 pi.
E, because the expansion parameter is square over 16 pi square, right? Or alpha over 4 pi. Okay. And this property is actually quite satisfied in concrete situations. For instance, in QCD, in low energy QCD, you have precisely a situation like this where the scale lambda here is lambda QCD, if you want, or if you want to be concrete, the mass of the rho, and below this scale you have precisely an expansion like this, where instead of phi you have the pions, and people have gone to very high order in the study of that because this matters in low energy experiments or flavor physics, when you study pion scattering, kaon interactions. This is a very sophisticated area of physics, which recently just got a big blow because the main experiments doing kaon physics was cancelled at CERN, just to be a big dump, okay? And anyway, this is okay. In this situation, and this NDA was invented by Georgi, was remarked first by Georgi, Randall, and Georgia Emanuel, and was later made more clear by Cohen, Kaplan, and Nelson, where they termed NDA an inexact science, but a useful art. Okay, but anyway, going back to.
But here, kind of when emphasizing this point, you mean that one distinguishes 4π from 1, right? So that's
yeah, this is 4π from 1. Yeah, and when you, for instance, when you do composite Higgs, you can say, oh, this is composite, and 4π. If you put 4π, you get too big Higgs mass. So yeah, 4π probably is less. I mean, the coupling of a composite theory is probably better 2 or 3, and which is also interesting because, like in QCD, the coupling of QCD, the G star, is what is it? Well, it's a coupling that should become strong, that is the maximal, when the gauge theory has the minimal amount of colors. And in that case, it goes precisely like 4π over n color. Okay? And in such a way that the loop expansion parameter, G star over 4π, is precisely 1 over n color. And in fact, if you look at the mesons have multiplicity that go like the number of flavors. So actually, when you add the flavors, the expansion parameter with the flavor multiplicity is NF over NC, which is interesting because when NF is much less than NC, this expands very well. But when NF crosses NC, something happens. What happens when NF becomes bigger than NC? Confinement fails. Because when you have, and the whole description in terms of confined object, for example. And that, in a sense, you already see in this silly way. Anyway, in QCD it works nice. In the electroweak theory, you have an effective theory, which is Fermi theory, and there the coupling is the weak coupling, and it's much less. It's about over 1. Okay. And these are all empirical examples. There are also theoretical examples. There is this famous solution of n equal to SU2 gauge theory in supersymmetry by Seiber-Witten, where they give an explicit expression for the prepotential, okay, which is a term in the action which has 2 derivatives and arbitrary number of fields. So the terms that come with 2 fields, 4 fields, and more fields, when weighted by the scale of confinement, I'll give you precisely in a segment of G star, and you can check in the G star you get in that case, it's an SU2 gauge theory, is precisely over 4π. Okay. So that's just a useful. Anyway, I can tell you that. Now, what did I want to say here? Now, I want to give you their G-flow picture. So I want to, so this request here, okay, is based on the fact that I really want to know what I'm doing with this Lagrangian, okay? But actually, it turns out that you can think of an abstract situation, and in this situation, requiring this simply amounts to requiring that this set of fields is weakly coupled at energy below lambda, okay? Which just follows from the fact that you have constructed this Lagrangian in terms of concrete fields, and you're doing computation with those fields. But there's actually, you can actually argue that the situation I described here of effective theory applies more generally. And let me explain. Okay? Let me tell you, give you, and this is the last thing I am saying today, and fortunately I'm afraid I will not say it completely, so I will finish it tomorrow. So this is the RG flow picture of effective field theory, effective quantum field theory. Okay. So let me review a little bit what we did. So we consider a situation where there is some ultraviolet scale lambda, which is a microphysics scale. Inverse lambda is a microphysics scale, and here is where things go wrong. Okay, here the thing breaks down. Okay, there is the lion. You're eaten by the lion. Okay, the description breaks down, and this is energy. Okay, and then there is a much lower scale, which is characterized by the mass m. Okay, and we describe physics in the between. Okay, how can we can say something more about physics in the between? As I said, the Lagrangian is written. Let me just go to the general case where we have all terms, even the odd terms in phi. So there is. Let me eliminate the tadpole for the sake of the argument. I can always get rid of it by defining the field. Then there is some g cube, phi cube, g4, phi 4, g5, phi 5, g6, phi 6, and so on and so forth, and higher derivatives, okay? And as we argued, based on the dimensionality of these terms, there are terms that have dimension whose operator dimension less than 4, which is to say that the couplings have positive dimension. This is dimension 2, this is dimension 1, the cubic. Then there are terms that have dimension where the couplings have negative dimension, dimension -1, this dimension -2, and so on. And then there is the one with dimension 0, the quartic coupling with no derivatives. And assuming that there is a big separation between lambda and m, in fact, it turns out that this G3 cannot be, should be less than, let me say, 4 pi m. If that is not the case, the vacuum where you are sitting at, so even if this is not positive sign defined, you have a potential like this. If that is not the case, if this is not the case, here you will tunnel out instantaneously, essentially, on a time scale which is of the order of the inverse mass of the particle. So you need to have, so in other words, this cubic is essentially not bigger than the mass, so they scale the same way. In other words, anyway, so you have the mass, you have the cubic, and these guys are all important at low energy. The relevance is measured by dimensionless quantity that are something like this. Okay, so this becomes important at low energy. Let me call these guys. Yeah, let me call this. Yeah, and these other guys are instead a positive power of energy, G5e, G6e squared, and these become important at high energy. And while there is this one here, which goes like G4 e to the 0, at least at the first naive level order. Okay, so you, again, this is what I said before. You have 3 classes of couplings. The irrelevant ones, they become important high energy and unimportant low energy. The relevant one and the marginal. Okay, and now the situation. What is the situation? The situation is that when you first start, you have to imagine doing what we call an RG flow. You just compute some quantity, okay? Compute a scattering amplitude, and then change the energy, and see how this quantity changes. Okay, just rescale. You just do several times the experiment, and you're like taking a trip on the highway from one tool booth to the next. Okay, and you cruise in the middle. Okay, and so you go through, So when you start, and you start decreasing the energy, you start a situation where you are in a very messy situation. It's like when in QCD you start with energy of order the raw mass, it's a mess, you see the resonances, you see all the structure, you see what, you see what this thing is. But as soon as you go to low energy, the effect of these guys quickly subsidizes, okay? And then, if the separation is very large, before these other guys become important, these guys become important only at the very end, when you get to energy of order m. But for a large swath of energies, okay, when the energy is much less than lambda and much bigger than m, all that there is to describe physics in first approximation is the part of the Lagrangian which involves coefficients without any dimension. Plus small. This effect that I write small here, they are either these guys that are dying out when you're going to low energy, or the mass and the trilinear that have not yet grown large enough to bother you. Okay? So in this intermediate region, physics is described by this Lagrangian. And now, if you look at this Lagrangian, you realize something, that it allows you to extend this situation beyond this simple case where we're dealing with weakly coupled field. So what is the main property of this Lagrangian? Notice it's already said there. This Lagrangian, while you're cruising from high energy to low energy, keeps being important. Okay? It's not dying off like these ones. So in other words, its effect are largely scale independent. Well, they're scale independent because to assess the importance of G0, you simply have to multiply by 0 power of the field and of the energy, and this doesn't have any energy. So what is the crucial property here? The crucial property here is that this Lagrangian is scale invariant. Okay? So you have a situation where you start with some messy short distance physics. There is some far infrared where you will notice that there is a mass in the cubic, okay? God knows why these guys are small, okay? As I said, if these guys were not much smaller than lambda, I wouldn't know what I'm talking about, okay? I would be like doing, without any offense, because these are very, biology or chemistry, it's a mess, right? I don't have a separation of scale, okay? While as physicists, we like to study absolutely simple things, and we're allowed to do that when we have the separation scale. So what happens in the middle? In the middle, you have a Lagrangian that is invariant under scale transformations, namely phi of x going to say, we call it lambda, although it's not that lambda. How do I call this? Yeah, we call it lambda. Lambda is a parameter, okay? Okay. So in this intermediate regime, and that's precisely the measurement of the fact that nothing really dramatic happens. If you want, what you have here is a sort of desert, okay? Now, in reality, in this situation here, in this particular theory here, phi to the fourth, the fact that you have the scale invariance is only true at the leading order in G4, okay? While you cannot have any negative or positive power of E coming from G4, compatibly with having a dimensional expression of E, you can get logarithms of E, okay? In other words, in this regime, physics, as long as G4 is small, depends in a weak logarithmic way on the scale, okay? So in other words, in this regime, the theory is not scale invariant, but is to a good approximation scale invariant. So in other words, in this regime, the theory is approximate scale invariant. Now, let me conclude. I take 1 minute. Now, this suggests, and I will discuss this tomorrow, that the situation that we're envisaging here in this theory with this scalar field, with this detailed little model, has actually a more general validity. What can happen is that, and we have examples of that both theoretically, for instance using supersymmetry or ordinary gauge theories, and in condensed matter, what can happen is that what you have is that you have some complicated physics here, and the physics that emerges here is given by an approximately scaling invariant Lagrangian action. Okay, but the scaling invariant Lagrangian, in general, doesn't have to be weakly coupled. Okay, it can be a very strongly coupled Lagrangian, and again, the situation will be that you have this leading, that in the between, you will have this leading scaling invariant term, and then you have the sum of two classes of terms, gi OI, where the dimension of OI is less or equal than less than 4, okay, and the sum of GA OA, where the dimension of OA is bigger than 4. So this is again irrelevant and relevant, okay, and we know of situation where this theory, that this description that works in between these two very separated scales is just the only thing you can ask. Okay, the very fact that I have a situation where nothing really happens between these two scales tells you that in first approximation the theory is scaling invariant. But scaling invariance doesn't need necessarily to be weakly coupled. Okay, so what we have here, we have the particular case of a scaling invariant theory, a theory which is essentially free. Okay, and in fact there are lots of examples that the standard model itself is an approximately free. It's an approximately free scaling invariant theory. Okay, it has. If you look at if you treat the coupling, if you see the standard model couplings, at least at energy about 100 GeV, they're all very weak. So in first approximation, you can neglect them compared to the kinetic term, okay, because they're weak. And what you're left there is just the scaling invariant. Now, the main point I want to make here is that in reality, we can think, and if you want to think of model building, you have to try to think what are the essential ingredients. The essential ingredient of this story that the relevant guys go down, and before the other guys go up, there is scaling invariance. This doesn't have anything to do with coupling. It's more general. So it could be that situation of physical relevance of particle physics are of this type, where somewhere in the desert, theory is described by a scaling invariant Lagrangian, but not weakly coupled. Okay. And now it turns out that in all the relevant cases, the scaling invariant Lagrangian has a bonus, an additional sigma, that is the conformal invariance. And conformal invariance, together with scaling invariance in the Poincare group, makes a very tight structure that makes the theory in the between here very, very constrained. Okay, and these theories called conformal field theories are, in a sense, the quantum field theory analog of point particles. They are what is left when you say take this scale where the relevant coupling becomes important and you send it to 0, and you take this macrophysics scale and you send it to infinity. In this scale, in this limit, all is left is this limbo, where you are, it's like this heaven, if you want, where nothing happens, okay? Where there's no evolution, everything is just the same at all distances, the most boring thing. And so these theories are very, very constrained. They are the analog, they are the field theory analog of point mechanics, okay? And these are conformal field theories. And the interest of conformal field theories for particle physics just follow from this. Of course, conformal field theories are also interesting in a deep way to understand quantum gravity through the DS CFT. They're also interesting to understand things like, boiling water, okay, critical system in statistical mechanics, quantum phase transition. But they are the essence, they are the general perspective on separation of scales in quantum field theory, and they are an essential ingredient. Whenever you think of new physics, whether it's the hierarchy problem or other things, I was discussing dark matter some time ago with some of you, this is precisely the context where you are. Of course, free field theory is the simplest example, but it's not the unique. I will discuss this more tomorrow. Thank you.
Questions?
Oh, yes. Questions?
There's always